This video shows an Analog Devices AD9081 MxFE eval board in a beamforming receiver application. We'll be running QIQ Systems Quick Beamforming Receiver software. This video is a revised version of a previous one and fixes the errors in that previous version. Here's an overview of the video. We'll talk about the measurement setup and the waveforms that we'll be using, and then we'll go into running with QIQ Beamforming Receiver software. First of all, we'll do a calibration of the system, then we'll just do some basic operation to show how to turn things on and off. Then we'll do a couple of examples. The first one shows signal-to-noise improvements using a multi-antenna array, and then we'll talk about interference rejection improvements. Here's the measurement setup that we'll be using. On the left, you can see 4 antenna elements, a linear array with lambda spacing between the antenna elements. Each of those receive antennas feeds one of the ADCs on the eval board. On bore site, we have a transmit antenna, which is being fed by DAC 0, and then 30 degrees off of bore site, we have another transmit antenna that is being fed by DAC 1. As I said, this is using the Analog Devices AD9081 eval board that's being hosted by a Xilinx ZCU102 host board. Here are the waveforms that we'll be using. The bore site transmit antenna will be sending an 8 PSK 12.5 megasymbol per second signal being fed by DAC 0. And for the 30 degree off bore site transmit antenna, we'll send a 2-tone with 10 megahertz spacing being fed by DAC 1. We're thinking of this as a jamming or interfering signal. After starting up QIQ Beamforming Receiver, first we go to the instrument menu and bring up the instrument connection dialog, make sure that we're talking to a 9081 over the network at this IP address. And then we also go back and instrument AD9081 control. So let's make sure that we have DAC 0 turned on. For the moment, let's turn on all of our receive antennas. Let's capture 40,000 samples with each of the ADCs. Center frequency of 2.4 gigahertz, and we're using a 250 megasample per second IQ data rate in and out of the AD9081. Before we do any measurements, we should do a balance calibration for the system. Balance calibrations deal with the imperfections of different antennas, different cables, different receive channels, and balances those out. It makes a measurement, and then we can compensate for those differences. So I bring up the balance calibration dialog. We're going to do 3 frequencies from 2.3 gigahertz, stepping in 100 megahertz increments. We're going to reference everything to channel number 1, and here's a file that will store the results of the calibration in. So we just go up, make sure we're in balance calibration mode, and hit the start button, and it does the calibration, and it's all done. Now let's call up some transmit waveforms. So we go to File, Transmitter Files. On transmitter 1, which is going to be DAC 0, we've got that 8 PSK waveform. On transmitter 2, that's going to be DAC 1, we've got that 2-tone signal. And transmitter 3 and 4, that's DACs 2 and 3. There's no waveforms for those. And now let's go down to 9081 control, and let's just turn on one receiver at the moment. And let's be in spectrum analyzer mode, and let's hit the start. The top left plot here is the acquired spectrum for all of the individual receivers that are turned on. At this moment, we only have receiver 1 turned on, so we're seeing the spectrum that we get from that antenna, which is feeding ADC 0. If we have multiple receiver channels on, then we add them together and we have a combined spectrum, and that's down in this plot over here. You can see other signals popping up here. We're working right at the edge of the Wi-Fi band, and so this is some Wi-Fi activity that's happening at the same frequency space that we're doing these tests in. Over here is the antenna factor. This is plotting the pattern that the antenna is generating. We only have one receiving antenna turned on, so it's omnidirectional from -90 to +90 degrees. Bore sight is right here in the middle at 0 degrees. Down below we've got a constellation plot. When we start doing the demod of our waveforms, we'll see a final constellation of symbol points, and over here we've got some measured results. Now let's turn on some more of the receive antennas. So we go up to Instrument, AD9081 Control, and just turn on 4 of the receive antennas. And the first thing that you'll see is that this plot up here is now displaying 4 different traces with the different colors up there. And now we have an antenna array factor which is coming from 4 antennas with equal weighting and 0 phase difference between them, and this is what that pattern looks like in space. So that's the basics of how to set up QIQ Beamforming Receiver and how to use it. Waveforms, number of receivers, and so forth. Now let's go on and take a look at why people are using multiple antenna systems so often these days. So first thing I'm going to do is I'm going to go up and turn off all of the antennas except for one. And then I'm going to switch this over into PSK demod mode. And let me go down here, make sure that we're doing 8 PSK at 12.5 megasymbols a second. And let's hit the start button on here. So we're using one receive antenna, and so the summation of one receive antenna is this. The array factor is omnidirectional, and then here's the final symbol constellation. And just a couple of things to note here. Note that our carrier to noise ratio is around 28 dB. That is this power level here compared with the power level down here. That's called carrier to noise, and it's around 28 dB. Then finally, on the final symbols, we're also for EVM around -28 dB for the EVM level there. Now let's click on a second receive channel. So now there will be 2 antennas and 2 receive channels turned on. So you can see there are 2 plots up here, and down here the first thing that happened is the carrier noise ratio got about 3 dB better than it was previously. And here was the level of the noise previously, and you add 2 noisy channels together and it doubles that by 3 dB, so our noise level went up like this. But because the signals are coherent, we're also doubling the I and doubling the Q values of our modulation, so that goes up by 6 dB. So this went up by 6, this went up by 3, so that was a 3 dB improvement. So carrier to noise ratio is about 3 dB better, and our EVM is about 3 dB better now on the final symbol points. Here's the array factor of 2 antennas with lambda spacing in between them. And finally, let's switch over to 4 antennas. So we're going to double the number of antennas again. First time we doubled from 1 to 2, now we're doubling from 2 to 4. So here's our 4 antennas up here. Here is the summation of those together. And again, our carrier to noise ratio improved by about 3 dB. And our EVM also improved by about 3 dB. So that's one of the benefits of using multiple antennas. As long as you have them phased correctly so that your I and Q values are adding together, you do add the noise from all of these together, but noise goes up by 3 each time, and the IQ the signal level goes up by 6 dB each time. So every time you double your number of receive antennas, you improve your signal-to-noise ratio by 3 dB. Another benefit of using antenna arrays is this antenna factor, this pattern that receives energy in some directions and rejects energy coming from other directions. So let's do an example to see what that looks like. Let's go up here and turn on our antenna at 30 degrees off bore sight. That's that two-tone signal that we're thinking of as interference or jamming. And let's start out with just one receive antenna. Okay, so here is our receive antenna. It's getting a signal from bore sight, which is that 8 PSK waveform, and it's also getting a signal from 30 degrees off bore sight, which is that two-tone jamming signal. And this two-tone signal is impeding our ability to do a demod. We're trying to do an 8 PSK demod, but it just can't happen because that two-tone is messing up the mathematics in there. So let's double the number of antennas. Let's go to 2 receive antennas. So the first thing that happens is by using 2 antennas, we create a null at 30 degrees. And so you'll notice that each individual antenna, receiver 1, receiver 2, each of them is receiving both of those signals. But when we add those together, we are suppressing the two-tone signal, and all of a sudden we're able to recover our waveform of interest. So this is the 8 PSK waveform. It does show a little bit of an artifact that there's something else there, but nonetheless we could do a good demod on this, recover it without symbol errors or bit errors resulting. Likewise, if we go and turn on 4 antennas, there's not a lot of improvement here because we already had a null at 30 degrees from 2 antennas. So there may be a little bit of improvement in the signal-to-noise ratio in this case, but in terms of suppressing a jammer, 2 antennas was good enough to create a null where our jamming signal was. Alright, that's it for this video. We've used QIQ Beamforming Receiver and the Analog Devices AD9081 to demonstrate a 4-element array. First of all, we saw that we improved the signal-to-noise ratio using multiple antenna elements, and then we saw the benefit of focusing the antenna array factor to suppress some jamming or interference signal. You can visit us online at our website at qiqsystems.com, or you can contact us through sales@qiqsystems.com. Have a good day.